All right, so next we're going to be talking about energy conservation. Energy is constantly transforming but never disappears. The law of conservation of energy is energy cannot be created or destroyed, only changed from one form to another. All right, so what this means is that the energy, you may have heard something similar to this here, is called the law of conservation of matter, where matter cannot be created or destroyed, but it can change forms from one form to another. Energy is the same way, in that energy cannot be created, destroyed here, but you can convert from one form to another one here. And so, kind of going back to when we were discussing about the major forms of energy. And so, with these different forms of energy, they're all energy, they're all measured in unit of joules. They all are able to cause some sort of change, whether it's a change in position or a change in its chemical makeup or a change in its temperature. Any type of change taking place here, these are all require some form of energy. So you can take thermal energy and convert it into mechanical energy. That's basically what a steam engine is. You can take mechanical energy and convert it into electrical energy. That's what a generator does. You can take, it sounds kind of weird, but you can take electrical energy and convert it into chemical energy. That's something in chemistry that we call electrolysis. You can even take some of the different forms of energy and turn it into nuclear energy, where some X-ray machines work off of that principle. You can take nuclear energy and convert it into thermal energy. That's what a nuclear power plant does. And then the same thing here, where thermal energy can be converted into any electromagnetic energy, where you're turning on your light bulbs. So all these different forms of energy here are able to be converted from one form to another one here. So, but the total energy still remains the same. We're just converting it from one form into another form. You can sometimes even turn it right back. So, going again with the energy conservation. So when you're looking at what's called potential and kinetic energy are constantly transforming back and forth. So most of the time during this transformation, some energy is turned to heat, sometimes also sound, and sometimes even light, and transferred out of the system. Now, because it's difficult to actually capture the energy of heat or light or even sound, a lot of times those energy are basically lost to the system or lost to the universe. You don't always are able to capture all the energy that was originally within the system. So this gets into a little bit of some of the mathematics behind energy conservation. The total energy of a system remains constant. So if you look at the formula here, the total energy, or sometimes you'll see this E sub T, or the total energy, is equal to the kinetic energy plus the potential energy plus the energy of heat plus the energy of sound plus the energy of light plus. So if you take into account all the different forms of energy, if you add all these different forms of energy together, there will be a constant total energy within the system. Now, many times, stuff like heat, sound, light, they're going to be very small, hardly even noticeable. They don't play that big of a role. And just to make things a little bit easier, a lot of times these other forms of this, what they call dissipative energies, are ignored. So generally the dissipative energies are ignored, and the form is simplified to simply the total energy is equal to the kinetic energy plus the potential energy. So there are other forms of energy, but to simplify things here, a lot of times we just look at kinetic and potential. The sum of these two will equal the total energy of the system. Since the total energy of a system is constant, if you know one of the values, for example the speed or height, the formula can be rearranged to the following here. So you can take potential energy is equal to kinetic energy. Well, potential energy is equal to mass times gravity times height, or mgh. Kinetic energy is equal to 1/2 mass times the velocity squared, or 1/2 mv squared. Since these two values are equal to each other, we can say mgh is also equal to 1/2 mv squared. Now, if you kind of reflect upon your math here, if you notice you have mass over here and also you have mass over here. These two masses, when you start rearranging it, these two masses will cancel each other out. So it simplifies down to gravity times height is equal to 1/2 v squared. So next, I'm going to show you how do you go about something for height and how do you go about something for velocity. Because once you have this form right here, what this allows you to be able to do is if you know how fast something is going, you can figure out how high will it go. For example, if you know how fast an arrow has been shot out of a bow, you can figure out how high will it go up. Or if you know how high a ball was dropped from a building, you can figure out how fast will it be going right before it hits the ground. But the other kind of a neat thing about this is, if you notice, mass has canceled out, which means mass does not matter in this type of situation. So if you take a playground ball and a bowling ball, and you both drop them, if you drop them both at the same height, even though they have two different masses here, they'll both hit the ground at the same time, traveling at the same speed. Or if you were to have something on a steep incline going up, and you roll a bowling ball 10 miles per hour from your hand, and at the same time you also roll a playground ball 10 miles per hour going up the same incline, as long as they're both going the same speed, they'll both go up to the same elevation up on the hill. So the mass of the object does not matter. Now, if you start taking into other things here, like friction and those things here, those are basically forms of some of the other dissipative energies here. But ignoring all of that, they both will act exactly the same. So let me show you how to go about rearranging this equation right here to either solve for the height or solve for the speed of the object. And we're going to be using that later on to do some calculations. All right, so let's go ahead and solve for the formulas for potential and kinetic energy when we're trying to solve for what is the height and what is the velocity of the object. So starting off, where potential energy is equal to kinetic energy. So conservation of energy, the total of energy at the beginning, will equal to the total amount of energy at the end of it. So potential energy, if you remember, is equal to mass times gravity times height. Kinetic energy is equal to 1/2 mass times velocity squared. So potential energy, if you're talking about gravitational potential energy, has to do with how high is the object. So the higher up it goes, the more energy, the more potential energy it has. Kinetic energy mostly depends upon how fast is it going. But also if you increase the masses, that would also increase the energy. Now, since these two values are equal to each other, we can take these two equations and rearrange them and solve for other variables as well. So for example, if you want to be able to solve for the height, if you know how fast something is going, you can find out how high can it go up. So let's take this equation again. mgh is equal to 1/2 mv squared. I'm going to leave the mass inside here just to show you how the masses cancels out and where the mass really doesn't matter as to how high or how fast an object is going to be going here, because in the end, the masses are going to cancel out anyway. So let's say you want to solve for the height. Now, height is being multiplied by mass and gravity. So let's get rid of these two. Since it's being multiplied to these, in order to get rid of them, you have to divide them out. So I'm going to divide out mass and gravity on both sides. Okay, now, if you notice, over here, mass is in the numerator, mass is in the denominator, it cancels out. Gravity is in the numerator, gravity is in the denominator, they cancel out. Over here, mass is in the numerator, mass is in the denominator, they cancel out. Nothing can cancel out the g or anything else. So what we're now left with is the working equation where height is equal to, now there's a few different ways, is I can either leave it as this, is 1/2 v squared all over g. That's one way of writing it out. If you don't like it that way, another way this way, height is equal to, you can go 1/2 v squared over gravity. You can write it out that way. Or another way you can also express it here is height is equal to velocity squared all over 2g. And I would recommend putting this in parentheses on the denominator. So all of these are exactly the same thing. Now, I'm not sure which format you prefer, but either way, any one of those will do exactly the same thing. In other words, if you know how fast something is going, take the velocity and you square it. Then you divide it by gravity, which a lot of times is going to be 9.8, and then you're going to take 1/2 that amount, or 0.5. It's the same thing over here. If you take the velocities, you square it. And then one thing I would recommend doing is divided by, open parentheses, 2 times 9.8, close parentheses. So these, by knowing how fast something is going, you can then figure out how high will it go. And again, all three of these formulas are exactly the same. I'm just not sure which format you're more comfortable with. Now, let's go back to the equation up here. And let's say this time you want to go the other way and you want to solve for how fast will it go. So if you know how high it was dropped from, then you can find out how fast will it be going at a certain elevation. So let me rewrite the equation again. mgh is equal to 1/2 mv squared. And this time we're solving for the velocity. I'm not sure how you were taught in your math class here, but since 1/2 and m are both being multiplied to v squared, I need to divide these two values out. So in order to get rid of 1/2, the opposite of 1/2 is 2. So I'm going to multiply both sides here by 2. You may have been taught a little bit differently here. It still works out the same way. So 1/2 and 2 cancels out over on this side. On this side, I end up with 2 mgh is equal to mv squared. Now, so I'm getting a little bit closer here. I was trying to solve for velocity. I need to divide out the mass. So I need to divide both sides by mass. And over here, the mass will cancel out. And over here, the masses will cancel out. And if you notice, as it was mentioned in the notes, is that we end up with where masses disappear. And again, that has to do with the mass of the object does not matter. So whether you're talking about a playground ball, a bowling ball, a Mack truck, anything of that sort here, the mass does not matter. Now, we're almost done here. We want to solve for the velocity, not the velocity squared. So I need to get rid of this square. The opposite of a square is a square root. So I need to take the square root of both sides. So I need to take the square root. What you do to one side, you need to do to the other. So the square and the square root will cancel each other out. So you're finally left with velocity is equal to the square root of 2 times gravity times height. And so this is the final equation to solve for velocity. So in other words, if you know how far something was dropped, and again, gravity is going to be the acceleration due to gravity, which is going to be, a lot of times, going to be 9.8 meters per second squared. Or if you're dealing with imperial units, it would be 32 feet per second squared. And you double it, and then take the square root of that value. That will let you know how fast will it be going. So if an object is falling down from any type of elevation, if you know where it was dropped, you can find out at any elevation how fast it will be going based upon this equation. All right, so next, we're going to be taking these two equations and start applying it to some example problems. You'll need your calculators.